Alright, lesson 6.3, Parametric Equations and Motion. Now, we are starting this lesson jumping into a new way of thinking about equations that has to do with parametric equations. Normally, up to this point, we've dealt with standard functions or standard relations. Now what we want to do is start defining x and y as functions of a third variable, t, called the parameter. Now, x, y, and t, again, are just letters in the alphabet. They don't have to be x, y, and t. They could be any three letters. T, though, is just like x and y, is the most common variable that we use to represent a parameter because it's t with respect to time. Think about objects that are moving through space. They have a horizontal position, they have a vertical position, and we can describe the horizontal and vertical position independently of each other in terms of a third variable, time. At a particular time, I'm at a particular location along the x-axis, I'm at a particular location along the y-axis. So it's simply a different way of describing location. Instead of x being the input and y being the output, t is the input, both x and y are outputs. So again, the old way of describing functions would be as a rectangular, also known as a Cartesian equation. In other words, y is a function of x. X is your input, y is your output. The new way is a parametric equation, where instead of just having one input and one output, we still have one input, which is t, but we have two separate outputs. Y is a function of t, x is a function of t. Now notice I use different letters to represent each of the functions because again they do have to be described as different functions. Y is its own function, I called it f. X is its own separate, completely independent function. We'll call it g just because I can't call it f. Now we have a parametric interval, which is just a fancy way of saying the domain. When we were in Cartesian equations, x represents your domain, y represents your range because x is the input and y is the output. With parametric functions, t is your input, therefore your domain should be with respect to t. So sometimes we'll refer to it as the domain, other times it's referred to as the parametric interval. It really doesn't matter which word you use. So we can just say t is between a and b. Just like any domain could be written as between two numbers a and b, t can be written that way as well. Alright, now because one of the beauties of parametric functions as opposed to Cartesian functions is that it has implied direction. When I'm graphing an equation y with respect to x, for example, if I'm graphing the equation y equals x squared, I have a parabola that kind of goes up both to the left and to the right, and it expands to the left and to the right. So it really doesn't have direction. It kind of goes in both directions at once. Whereas a parametric equation, I could graph the same parabola, but I can give it direction because t would be graphed either from left to right or right to left, depending on the t interval given and depending on the specific parametric equations given. So, in other words, a parametric function will specifically have an initial point and a terminal point. Initial point is simply taking the leading value of the domain and plugging it in. So in other words, I'd get the coordinate g of a, f of a, because of course g represents your x value, f represents your y value. And we get a terminal point, g of b, f of b, representing where the parametric interval ended. Alright, now one of those things we like to do in math classes is we tell you, hey, here's something new, but really it's not new because we've been doing it all along. Parametric equations is a perfect example of that. The unit circle is actually an example of parametric equations. Now recall that the unit circle is just a circle centered at the origin with a radius of 1. That's why we call it unit circle, because the radius is 1. XY just represents some random point on that unit circle. Now remember, the Cartesian or rectangular form of that equation was just x squared plus y squared equals 1. Because of course again the center is at 0, 0 and the radius is 1. But we can also use a parametric form to describe that exact same circle. And the parametric form is once again something you've been using all along. X equals cosine of theta, y equals sine of theta. In other words, x and y are defined completely independent of each other, both with respect to some third variable, in this case theta, representing the parameter. So theta represents your input, in other words the angle that you're calculating. X and Y represent your output because, of course, that's just the location on the coordinate plane, the XY value. And, of course, we have a parametric interval. For the unit circle, theta would go from 0 to 2 pi. Now notice we don't include 2 pi in that interval because for the unit circle we only have to include one of the endpoints, 0 or 2 pi. We'll typically include 0, not 2 pi, again because they're at the same location. No need to include both of them. So we've been doing parametric equations all along. X is a function of theta, Y is a function of theta, theta is on some specific interval. And we could also graph that using the calculator. So here's an opportunity for us to learn how to use our graphing calculators in a new way. Now, of course, there's the old way. I could graph it using the Cartesian form, x squared plus y squared equals 1. But the problem with our graphing calculators, if I were to try to graph that, it's a y equals screen on the calculator, yet this is not in form y equals. So we just have to quickly algebraically fix that. Move the x squared over, take the square root. I would have square root of 1 minus x squared, which I could go ahead and plug that in, but the problem is that would only give me half of my unit circle. Remember, when you take a square root, it's positive or negative, so I would have to include both options, one in y1, the other one in y2. So then I could graph it, but before I graph it, I'll go ahead and adjust my window. Now, it's a unit circle, the radius is 1, I don't need that big of a window, so I'll go ahead and do my x scale from -3 to 3 and the y scale from -2 to 2. Now the reason I don't just use the same values on both is because your calculator screen is a rectangle. If I graph the same range on both the x's and the y's, then my circle is going to look elongated when in fact it's supposed to be a circle, not an ellipse. So what I do is I'm just going to adjust the x values, make the x values a little bit longer than the y values because, again, it's a rectangle. It's longer in the x direction than it is in the y direction. And specifically, your calculator is at a 3 to 2 ratio. The length of the calculator to the height of the calculator is 3 to 2. So as long as your window is always at a 3 to 2 ratio, you will always see your graph in the correct proportions. Alright, so I'll go ahead and graph that in my calculator, and this is what I'm going to see. I'm going to see a circle, yet it's not going to be fully connected at the x-axis, and that just has to do with the quality of the calculator. If you have a more expensive calculator, keep in mind I'm using a TI-83, 84s would look exactly the same. If I had a more expensive calculator, a fancy calculator, it probably wouldn't do this, but the problem is these older calculators don't always calculate correctly. So this is a situation of your calculator lying to you. You have to know that what you're graphing is a circle in order to realize that, yeah, this is really supposed to connect. It's just a weakness of my calculator that it's not connecting. Now, I say that's a weakness of a calculator, but it's also a weakness of Cartesian forms of equations. If I want to graph a circle, putting it in that y equals makes things a little bit more cumbersome, makes things a little bit more complex, makes things a little bit more difficult. Circles are much easier to graph using parametric or, when we get to it, polar functions. So that's what I'm going to do. Let's go ahead and redo this, but using the parametric form of the circle. Now again, that parametric form was x equals cosine of theta, y equals sine of theta on the interval 0 to 2 pi. So what I'll do is I'll go ahead and pull up my calculator again, but this time I'm going to switch my mode into parametric. So if I hit the mode button, and then it's just the fourth row down, second button, PAR stands for parametric. Now in the future we're going to be looking at this one as well. This is the polar mode. Sequences was from a previous chapter. But notice there are 4 different modes here. If you look at your calculator, if we've ever wondered why there were 4 different letters right here on this variable key, it's because of those 4 different modes. Depending on which mode you are in, that variable button is going to change. If we're in function mode, if I hit the variable button, I get an X. Parametric mode, it's going to give me that T. Polar is going to be theta. Sequence mode would give me N. So depending on which function or which mode I'm in, that button will say a different thing, but it always means the same thing. It's just your input variable. So once my calculator's in parametric mode, I can go ahead and pull up the y equals screen, but now instead of it being y equals, because it's parametric, it's x and y equals, because each function is going to have 2 components, the x component, the y component. Now notice right here it says t all the way down. That's just to kind of remind you what your input variable is going to be. When I hit that variable button, it's going to come up as a t, even though this says theta. Remember, the letter is irrelevant. It's an input value. You can call it whatever you want. So when I type the two functions in, I get cosine and sine. Again, it's t, not theta, because the calculator is only going to give you one option. I'll go ahead and go to my window just like I did before, but notice when I pull up my window, I'm going to see something new. I'm going to see t-min, t-max, t-step. The x's and y's are still going to be the same as to what we put in before, but now we're going to have that t variable. Because we've got three variables now, my window needs to compensate for that. Now again, this is where we're going to put in our parametric interval. We're going from 0 to 2 pi, so I'll just type 0 to 2 pi, but hopefully you'll notice as soon as you move away from that 2 pi, calculator's automatically going to convert it to decimal for you. 6.28 is just 2 times 3.14. Alright, and then as far as the t-step goes, make sure that number is small. Most likely when you pulled it up, it probably said something about 0.13. That's perfectly fine. You can leave it like that. I typically type in 0.1 just so I can be consistent. We want that number, that t-step, we want that number to be small, but not too small, and of course not too big either. Basically what your calculator does when it's graphing, it plots points. That's all your calculator knows how to do. And that t-step tells the calculator how often to plot a point. So in other words, the calculator is going to start by plugging in t equals 0, then it's going to plug in t equals 0.1, 0.2, 0.3, 0.4, 0.5, all the way up to 6.28. So that's going to give me a nice reasonable graph. It's going to give me a lot of points, and my graph is going to be fairly accurate. So if I made that t-step of, instead of 0.1, just to be 1, then it would have graphed at t equals 0, t equals 1, t equals 2, t equals 3, all the way up to t equals 6. It would have stopped right there because t equals 7 would be too far. So it would have only given me a handful of points and then connected the dots. My graph wouldn't look very good. If I made that really small, 0.00001, it would be plotting so many points that the calculator would take forever to graph it. I encourage you to play with that little t-step on your own, make the number bigger, make the number smaller, so you can see what I mean. Alright, so I'm going to leave it as 0.1. And when I go ahead and hit the graph, I should get exactly this. So here's my circle again. Notice it doesn't have the little blips near the x-axis, because this is a much more efficient way of graphing than within function mode. And one of the beautiful things about this is if I graph my unit circle in parametric mode, it allows me to cheat. So watch this. So I'm going to go ahead and pull up my calculator. Let's go ahead and switch it to parametric mode. I got cosine and sine. Go to my window, adjust things, 0 to 2.8. My t-step is 0.1308996 and so on. I'm just going to go ahead and leave that there. No need to change it. -3 to 3 for my x's. -2 to 2 for my y's. Graph it. Here's my unit circle. Alright, now what I mean by allowing you to cheat is instead of having to, if you want to do some unit circle problems, now of course I assume you already have it memorized, but if you wanted a quick little reference as to, pick an angle, figure out what the trig ratio is on the unit circle, instead of having to find my trig chart, if I have my calculator, I can just use this, hit trace. When I input a value for parametric, remember I'm inputting a t value, and t represents your angle. So if I want to do, let's say 30 degrees, which again, my calculator is in radian mode, so that really means pi over 6. If I just type in pi over 6, it'll quickly give me the cosine and sine values at that angle of pi over 6. The sine value is 1/2. The cosine value is, it says 0.866, but my knowledge of arithmetic tells me, well, that's just the square root of 3 divided by 2. So, and I could do that all the way around. I could do 4 pi over 7. No, I'm sorry, 7 pi over 4. Seven pi over 4, of course, is the 45-degree interval in the fourth quadrant, which I expect to be root 2 over 2, which is exactly 0.707. Positive, negative, x and y. So it's just another way of going through the unit circle if you wanted to, or of course you could just, memorize it. Alright, let's keep going. Now what we want to do here is to graph a parametric equation. Here's the parametric equation: x equals t plus 1, y equals t squared plus 2t, on the parametric interval -3 to 2. Again, part A, we're going to graph the given relation in the xy plane because parametric functions are graphed in the same plane that regular Cartesian functions are graphed. We do it in the xy plane because we have an x value and a y value. The difference is parametric is based on an input value of t, but that t value is not actually part of the graph. The t value just tells you where to put the graph, not what the graph looks like. We're going to indicate direction of the curve, and we're going to do this without technology first to prove that we can do it by hand, and then we'll go ahead and pull out our calculators to go and check our answer. Part B, we're going to convert our parametric equation into a Cartesian equation by eliminating the variable. In other words, we're going to write it as an algebraic relationship between x and y, and then we'll ask the question, is y a function of x? If necessary, we'll state the new domain. Alright, so let's go through the first one together, and then the next couple you can try on your own. So we'll start with a graph. Now, just like you did on your, let's call it first day of Algebra 1 graphing, before you learn any specific techniques for graphing, the way you learned was simply to plot points. In other words, pick a number for x, plug it into the equation, figure out what the y value is, and that way you can just plot points on the graph and connect the dots to get the shape of the graph. And then as you progressed into your algebra, you learned more advanced techniques for graphing so that you wouldn't have to plot points every single time, which can be cumbersome and take a while. Well, when it comes to parametric equations, yes, you could do that, but we're not going to. We're just going to make it as simple as possible. We're just going to plot points every time. But it's not x values that you plug in, it's t values that you plug in, and you're going to plug it into both x and y. So instead of it just being a regular old t chart, I like to call it a pie chart. Alright, so I'm going to pick values for t. I'm going to plug it into both the x function and the y function. Those are going to give me coordinates on the graph, x, y coordinates on the graph, and then I will plot those coordinates in order that I listed the t's, because the order of the t's is going to give me the direction of the curve. So I'm going to pick values for t. Well, since I'm going from -3 to 2, it makes sense that I would list t values from -3 to 2. And I'll go ahead and plot at every integer between -3 and 2. Now, there is no general rule of thumb as to how many points you need. In general, the more the merrier. The more points you plot, the more accurate your graph is going to be. But sometimes it's a couple will be sufficient. My suggestion, 5 is a nice round number. Start with that, and if you need more, then plot more. So I'm going to go one by one. We'll plug in -3. -3 plus 1 is 2. I'm sorry, -2. -2 plus 1 is -1. And there's a little pattern here. It's just whatever the t value is plus 1. So I'll go ahead and fill those in really quickly. Y values will do the same thing. Again, start with -3. -3 squared is +9. Plus, that'll be -6. So 9 minus 6 would be 3. Then it would be 4 minus 4, which is 0. Then it would be +1 minus 2. Then it would be 0 plus 0. 1 plus 2. 2 plus 4. I'm sorry, 4 plus 4, which is 8. So here are my x's, here are my y's. Let's go ahead and plot them on a graph. I've got the coordinate -2, 3, -1, 0, 0, -1, 1, 0, 2, 3, 3, 8. Now let's look at it. Here are my points. Now it may look to you like this is a parabola. And in fact, you'd be correct. This is a parabola. If I were to connect the dots between my initial point -2, 3 and my terminal point 3, 8, I'm going to get this curve right here. I could plot more points just to be sure, but I think this was sufficient. Now, I say it's a parabola, but of course technically it's not a parabola. A real parabola should keep going up all the way, and then I put arrows to show that it goes all the way. But remember, we had a specific domain, a specific parametric interval of -3 to 2. That means this point is my initial point. I'm not going anywhere beyond that point. It starts right here, and then based on the direction of t, I'm going in this direction around the curve. And to show direction, I'm just going to put arrows along the curve. Notice I don't put arrows at the beginning and end like I do with Cartesian functions when I'm graphing those. When in that context, arrows mean it goes in this direction forever. In this context, arrows mean this is the direction of t, this is the direction of the graph. So don't put arrows on the end of the curve, because then you're telling me that's the direction of the graph. Now, of course, you technically could put an arrow on the end of this curve, but again, that arrow doesn't mean that it goes off in that direction forever. It does stop right here. It doesn't go any further than that point. But if you put an arrow over here, now you're telling me two different things at once, which makes no sense. It can't go this way and that way at the same time. Don't put an arrow at the end of the graph unless you're signifying direction. Alright, so we've done this without technology. Now let's check our answer with technology. Let me see if I can pull my calculator back up. So once again, we'll go ahead and let's double check, make sure I'm still in all the right mode. Alright, we'll go to our y equals screen. Let's clear out what we had before. X equals t plus 1. Y equals t squared plus 2t. Check my window before I graph anything. Instead of going from 0 to 6.28, we want to go from -3 to 2. And I'll go ahead and adjust it back to 0.1. Now, as far as my x and y windows go, let's go ahead and just match what I had on here. X is going from 1, 2, 3, 4, 5, 6, so -6 to 6. And y is going to be going from 1, 2, 3, 4, 5, 6, 7, 8 high, but it was only going 1, 2, 3, 4 low. So -4 to 8. And let's graph it, see what we get. Alright, so looking at my graph, I see that it does begin there and end there. Actually, let's go ahead and adjust our window. Let's make that y a little bit higher than 8 just to confirm that it does in fact stop there. Let's go all the way to 10. Alright, so there it is. It stopped at 8. It began right here. It ends right there. As it was graphing, notice it started here and graphed in this particular direction and not in the reverse. So it looks like it matches. Alright, moving on to the next one. Alright, part B, then find an algebraic relationship between x and y. Is y a function of x? If necessary, state the new domain. Now, in order to convert my parametric into a Cartesian equation, it's simply a matter of eliminating the parameter. So anytime you see the word eliminate the parameter, that means convert parametric to Cartesian. And to eliminate the parameter, we just need to remember a little bit of algebra. When you were solving systems of equations, I have two equations here. I have an unknown in common, the t value, so it's just a matter of solving for t in one of these equations and substituting into the other one. Now, it doesn't matter which one you solve for t, but of course, just pick the easier one and plug it into the more complex one. So I'm going to solve for t in the x equation. That's going to give me x minus 1, and then I'm going to plug it into the other equation, just like this. So x minus 1 squared plus 2 times x minus 1. Now technically this is an answer. It is an algebraic relationship between x and y, but I can't help myself. I'm going to go ahead and simplify. X minus 1 squared is really x minus 1 times x minus 1. Foil it out. I would get x squared minus 2x plus 1. Distribute the 2. 2x minus 2. Combine like terms. We get x squared minus 1. Now, of course, x squared minus 1 is just a parabola shifted down 1. And if I look at my graph, well, that's just a parabola shifted down 1. It's exactly what I expected it to be. Is y a function of x? Well, since the graph passes the vertical line test, and I was able to solve for y and have an equation that would give me only one answer at a time, then yes, y is a function of x. So I can say yes. If necessary, state the new domain. Now here's where we need to pay close attention. Remember, domain is in terms of y and x, domain is the x values that are being used. I could just look at the graph and say, well, the x values go to as far to the left as -2, as far to the right as +3, so my domain is -2 to 3. Or I can use the parametric interval. -3 to 2 was the t values. All I really have to do is take my t values and convert them into x values simply by plugging the t values into the x equation. If I take -3 and plug it in for t, I get -2. If I take 2 and plug it in for t, I get +3. So there's my domain, -2 to 3. Now notice it says if necessary. If necessary means depending on the implied domain of the function. Now this is a parabola. It is a polynomial. The implied domain of a polynomial is all real numbers. Yet the domain of what I graphed is not all real numbers. Because what I graphed and what was implied are not the same, then that means I need to state the domain that I want. If I didn't state the domain, then I would have assumed it to be all real numbers, which would have been wrong. So had I graphed an interval that was all real numbers, then it wouldn't have been necessary for me to state the domain separately because it would have been implied. Alright, so let's look at the next problem. So, just like we did on the last one, you can try this one out on your own and then hit play when you're ready. Alright, so let's go ahead and graph it just like we did before. I'm going to pick a t interval. Now notice on this one t goes from negative infinity to positive infinity. So we have a domain of all real numbers, which means you can pretty much start and end where you want. Just make sure that you always go in order when you're picking your t values. So doesn't matter where you start. You could start at -2, you could start at -10, you could start at -1 billion. It really doesn't matter. Just start somewhere and pick a few points. Again, 5 or 6 sound reasonable. I'm going to be lazy. I'm just going to copy, cut, and paste my t-values from the previous screen so that I don't have to retype anything. So I'm just using the same intervals that I did on the last question for no particular reason other than I'm lazy. So I'm going to plug in -3 through +2 in both x and y. And here are the values that I got. And we'll go ahead and plot them on the graph and see what happens. -5, 6 is right here. -3, 3. -1, 0. 1, -3. 3, -6. And the next one was off my screen, so I won't worry about plotting it. And hopefully you see, if I connect the dots, it's a straight line. And again, based on those t-values and the direction in which I plotted those points, I must be going from left to right. Alright? And I could do this on the calculator as well. So I need 2t plus 1. I need -3t minus 3. My window, my t steps, since it's going from -infinity to infinity, now keep in mind I can't actually plot -infinity to infinity. So I could just pick a really small number for t-min and a really big number for t-max, but then my calculator is going to take forever because it's actually going to plot all those values. So I'm just going to go ahead and pick some reasonable numbers, -10 to 10 for my t-min and t-max. That way it doesn't take too long for it to graph. And as far as my x-min and x-max, let's just go ahead and revert back to our standard viewing window. If I hit zoom 6, it'll go all the way back to my standard viewing window. And actually by doing that, I think it actually screwed up my t's. So let's go back. Yep. So when I do the standard viewing window on parametric, it's going to just put it into the trig standard viewing window. So let's go ahead and readjust those t's. Again, I wanted -10 to 10. And graph it. Alright, and there's the line that I got right here. It's exactly what I expected it to be. It's going from left to right. And there it is. Alright, let's go ahead and do the other part. Converting into x's and y's. Again, I'll solve for t in one of the equations. Both of these are equally reasonable, so I'll go ahead and solve for t in the x equation just because that's when I'm converting it to y as a function of x, I want x to be the input, so I'll go ahead and solve for x, or solve for t in the x equation. And I get x minus 1 over 2. I could have also said 1/2 x minus 1/2. Take it and plug it in over here. Distribute the -3. I also went ahead and distributed the division by 2. Combine like terms, -3/2 x minus 3/2, which is, of course, exactly what I expected it to be. If I look at my graph, the y-intercept was -1.5, and the slope was -3 over 2. And hopefully it should be obvious that yes, this is a function. It passes the vertical line test. And as far as the domain goes, this is a situation where it is in fact not necessary to state the domain. The domain of the parametric function was all real numbers. The domain of a line is implied to be all real numbers. There's no need to state it separately. Alright, here's another one. Try it on your own. Hit play when you're ready. Alright, so we'll graph it first by setting up our t interval. This time, instead of going from -3 to 2, that wouldn't make any sense because my lowest t value has to be 0. We're also doing a trig function, and we're doing it in radians based on the t interval that's given. So anytime I'm doing trig, if you've got to plot points, the most convenient points would be values that are on the unit circle. And as far as the unit circle goes, I'm going to start with just using the quadrantals. Remember, it's the 16-point unit circle. There are 16 separate points I could use, but I like to stick with the 4 axes. Well, actually, technically 5 axes, because I'm going from 0 all the way to 2 pi. So 0, pi over 2, pi, 3 pi over 2, 2 pi. If those points aren't sufficient, then I can always go ahead and throw in, say, pi over 6, pi over 4, pi over 3, or intervals of that. So plugging those values in for x and y, I get this. Hopefully you did that all in your head, because again, these are unit circle values. You won't get a calculator on the test for something like this, so you should still be able to do this by hand or in your head. Alright, plot the points: 3, 0, 0, 3, negative 3, 0, 0, negative 3, and all the way back to 3, 0 at the beginning. And of course, hopefully you figured this one out. It's just a circle, but this time the circle has a radius of 3, which if you look back at the original equation, well, that looks like the parametric form of the unit circle. Instead of it being a unit circle, though, the radius is 3. If I had made this x equals 5 cosine and y equals 5 sine, it again still would have been a circle, but the radius would have been 5. Whatever this number is right here, this is the parametric form of a circle with radius, let's just call it a. Now, I could also turn this into an ellipse simply by making these numbers different. If this were 3 and this were 2, it would go 3 in the x direction, 2 in the y direction. Again, that's an ellipse, an elongated circle. Indicate the direction of the curve. We're going in this direction. And of course, we could do this on the calculator, but I'm going to go ahead and skip that. Hopefully, we've got that point by now. Let's go ahead and eliminate the parameter. Now, here's a situation where doing it the way we did on the other ones, not so fun. I do not suggest solving for t on this one and plugging it into the other equation. It's going to make it incredibly ugly and incredibly unobvious. On this one, anytime you have trig, you want to think back to your trig identities. There is a handy-dandy little formula that we could use to directly relate cosine and sine. And if you think about it for a second, you might come up with the Pythagorean identity. Cosine squared plus sine squared equals 1. And of course, it doesn't matter what order you write that in, it's a plus sign. So cosine squared plus sine squared equals 1, that's always true because that's one of my identities. Well, instead of solving for t, let's just solve for cosine and solve for sine. In other words, divide both sides by 3, and I would get cosine is x over 3, sine is y over 3, and we can take that and plug it in for cosine and sine. So cosine squared becomes x over 3 squared, sine squared becomes y over 3 squared. Clean it up from here, x squared over 9, y squared over 9, and then just multiply both sides of the equation by 9. It becomes x squared plus y squared equals 9. In other words, standard form of a circle, center at the origin, radius of 3. So, is it a function? Of course it's not. It's a circle. It doesn't pass the vertical line test, so no. And the domain, well, the domain of the parametric function goes from 0 to 2 pi, which itself graphed a circle from negative 3 to 3. So the x values would go from negative 3 to 3, which is the implied domain. If it's a circle of radius 3, I would assume that the domain was negative 3 to 3. So the domain of the parametric technically matches the domain of the Cartesian, therefore domain is not necessary to state. Now, think about it on the other hand. Had I given a slightly different example, for instance, had I given you a circle which only graphed, let's say, the right side from negative pi over 2 to positive pi over 2, so if I had given you the same circle but only given you the t interval from negative pi over 2 to positive pi over 2, this would have only given me a domain of 0 to 3, yet the implied domain would have been negative 3 to 3, so this would have been a situation where I would have had to state the domain separately because the actual domain didn't match the implied domain. So you just have to pay attention. If what's implied is what's shown, then you don't have to restate the domain. If what's shown is not what's implied, then you do have to state the domain. Let's go ahead and move on to projectile motion. Now, before we actually get into projectile motion, I want to talk very briefly about the derivation of the equations of motion. So if you have taken a physics class, then this is going to be very familiar to you. And you are more than welcome to go ahead and fast forward until you get to the screen that has the baseball player on it. But if not, this is some useful background information on where the equations that we're going to be using come from. Now, it's based on a couple of basic definitions. The first one is this definition of acceleration. And acceleration is just the change in velocity over the change in time. Anytime you see that little triangle, that's just the Greek letter delta. And in math and science, delta represents change. So acceleration is the change in velocity over the change in time. Now, change is just whatever your current velocity is, let's call it v, minus your initial velocity. This is sometimes referred to as v initial, or more commonly v naught. N-A-U-G-H-T. Naught is just an archaic term for zero. So this is v sub 0 or v naught, and it just means the initial velocity. So your change in velocity is just whatever your current velocity is minus where you started. Same thing with time. But if we're talking about initial time, it's very helpful just to consider, let's just call initial time 0. That way we don't have to put this t naught term anymore. So we can just say v minus v naught over t. So acceleration, v minus v naught over t. And it's important to point out that we are going to go ahead and assume that it's constant acceleration. If we allow acceleration to change over time, then these formulas don't really work out all that much. So we're going to go ahead and assume constant acceleration for all this process. Now, if I go ahead and take this formula and solve it for v, move the t over, move the v naught over, I get this handy-dandy little formula, which is velocity equals acceleration times time plus your initial velocity. So if I wanted to know the velocity of an object, if I know that it's constant acceleration, and I know what time it is, and I know what velocity it started at, then I can tell you what its current velocity is. Now, just like acceleration is defined to be the change in velocity over time, velocity is defined to be the change in the change in position over time. It's common to use the letter S to represent position because some of the other letters that we use for position, X and Y, are already being used elsewhere. The letter D can go either for distance or displacement, so I don't like to use the letter D. I like to use the letter S just because I like to use the letter S, because apparently using the letter P for position was just too obvious, so let's go with S for no reason at all. Now, just like we did before, I could say change in S over change in time, or I can think of another way to describe velocity, and that's with average velocity. If I wanted to average two velocities together, that's just a matter of adding them together and dividing by 2. Well, because we are assuming a constant acceleration, that was key to this problem, that means the average velocity and the instantaneous velocity, the velocity at any given point in time, are going to be the same. So I can go ahead and just set these equal and solve based on that. So I can move the delta t over. I've got v plus v naught over 2 times delta t. I can remember that v is really at plus v naught. Plug it in, so I've got at plus v naught over 2 times delta t. And that's going to be 2v naught. Separate the fraction into 2 separate parts. I've got at over 2 plus v naught. Now, this is the point where I realize, well, delta t is really just t, just like we did in the acceleration problem. Delta t, t minus t naught, assuming that t naught is 0. It's just t. If I were to distribute that t across, I would get t squared and v naught times t. And right here we have our position equation. Now, this really should say delta s still. I took the delta off the t and accidentally took the delta off the s as well. This just represents the change in position. If I want to make it just straight position, that's just a matter of detaching. So that delta s is really s minus s naught. Well, if I move the s naught to the other side, I have my position function. Alright, position given constant acceleration is 1/2 at squared plus v naught t plus s naught, where s is position A is acceleration, t is time, v naught is your initial velocity, s naught is your initial position. This handy-dandy little formula is going to be used over and over and over again when we are talking about projectile motion, so it's useful to memorize. Now, let's use that in terms of projectile motion and two-dimensional parametric motion. So imagine someone's throwing a ball. When he throws that ball, he's throwing it at some initial velocity. That velocity is going to change over time based on direction, but initially he's going to throw it at a velocity at some angle with respect to the horizon. So that is your given information. You're going to know how fast he's throwing it, you're going to know the angle, and you're also going to know the height of the ball. And I can use all that information to create a set of parametric equations to describe the path of that ball. And I can use that basic position function in order to do it. Now, velocity, your initial velocity, think of that as a vector. Alright, so you've got v naught, which is the magnitude, and then theta is your direction. Now that vector can be broken into two components, your x component, so I just called it v sub x, and your y component, v sub y. Now remember, v sub x and v sub y represent your velocities in the x and y directions. Because if you think about it, when you throw an object, the position in the x and the position in the y have nothing to do with each other, as do their velocities have nothing to do with each other. As you're traveling from left to right, you're just going to travel along in your merry way, but you're also going to be traveling vertically up and down, first up and then down, but that's not affecting how it's traveling from left to right. So we can separate it into those parametric equations using their velocities. Now, of course, v sub x is your x component, and we can think about what we did with vectors to figure out your velocity in that direction. Again, it's just your magnitude of the vector times the cosine of the angle for Vx, and then magnitude times sine for V sub y. Alright, now to get our x direction, or our x position equation, we'll start with our standard formula. But here's another thing we have to realize: as we're traveling from left to right, it's not accelerating at all. It's just traveling on its merry way at the same velocity forever and always. It just travels in the same direction without changing velocity. Now, of course, we're ignoring any friction due to atmosphere or wind or anything like that, just like we like to do in physics classrooms. Then we get out to the real world and everything's up in the air, literally and not literally. But in the x direction, there is no acceleration. You can't force it to go faster once it's left your hand. Alright, so we can go ahead and get rid of that acceleration term because that's going to be 0. And based on where I put the xy plane, your initial position is going to be 0 in the x direction. So in the x direction, the only thing that really matters is your velocity in the x direction and your time. In other words, distance equals rate times time. So v sub x is v naught cosine of t, and what we have there is our x position equation. We can do the same thing for y, but this time acceleration actually does matter because, of course, on planet Earth we have something called gravity, which is causing everything to accelerate straight down at a rate of negative 32 feet per second squared. Let's go ahead and fix that. Alright, now of course if you're in meters, then it would be negative 9.8 meters per second squared. But if we're sticking with feet, it's going to be negative 32. In a math class, we typically stick with feet. In physics, you'd switch to meters. So I can plug in negative 32 right here. V sub y is going to be this guy right here. And y naught, and y, the initial position, is just going to be the height of the ball. So right here we have our x and y parametric equations of motion. We're going to use these in order to map out a projectile path and make some predictions. Alright, Jebediah hits a ball at 4 feet above the ground with an initial speed of 135 feet per second at an angle of 25 degrees with the horizontal. So here are some questions that we want to address, but before we jump into that, we need to figure out what the equations are. And I'm going to use those two equations that I just derived in order to do this. So I've got 4 feet above the ground, my initial height, my initial velocity, and the angle at which that velocity occurs. So let's just take that information. I'll go ahead and plot it in the picture and write my equations. So remember, x is just velocity times time. Velocity in the x direction means I need to slap a cosine in there. So v naught is 135, cosine of 25. So there's my x equation. I can do the same thing with y. Again, acceleration is always negative 32, so you can always go ahead and start with negative 16t squared. Velocity times time, slap a sign in there because it's in the y direction. And then y naught is going to be your initial position in the y direction, which is 4. So these are the two equations I'm going to be using that can map out this particular path. So everything I do is going to be based on these two equations, so we'll want to keep those handy. Alright, part A says, what is the height of the ball after 3 seconds? Notice keyword height. I am talking about a height, which means I am only talking about the y component of the path. The x component has nothing to do with height. It doesn't matter how far you are from the initial point. All that matters is how high I am, so the only thing I need is the y equation. And the question is at 3 seconds, so let's just evaluate y of 3. So it's just a matter of pulling out my calculator, typing in my y equation with 3 plugged in for t, and I get my answer of 31.160 feet. I didn't need the x equation at all because, again, x and y are completely independent of each other. Question is height, I just need y. Part B, how far has the ball traveled after 3 seconds? When it says how far has it traveled, that's implying how far did it travel along the ground, in other words, in the x direction. So just like part A, I only needed the y equation, part B, I only need the x equation. So just like I did before, plug in 3 for t in the x equation, 367.054 feet. So at 3 seconds, it's 367 feet downwind, and it was 31 feet high at that point. Now notice, it doesn't tell me whether the ball is rising or falling at that point, so it could be 31 feet on its way up, or it could be 31 feet on its way down. Based on the context, I'm 367 feet away. I'm going to guess it's probably on its way down by now. Alright. Moving on, what is the maximum height of the ball? Now again, I just mentioned on the last step, I'm assuming at 367 feet it's on its way down, so it's probably reached its height prior to that 3 second point, but I can't be sure. But again, we are asking about maximum height. Alright, height again is the y equation. The only thing I need is the y equation. So here's the point where I can realize, well yeah, I'm doing a parametric equation, but I really don't need both parts, just one part. So I'm going to go ahead and answer this the same way I did way back in chapter 2 when I was asked for a maximum value. I want the y value of the vertex. A maximum value is the y value of the vertex, specifically the vertex of the y function. So to get the vertex of the y function, I'm going to remember that handy-dandy little formula, negative b over 2a. Negative b over 2a would tell me the x value of the vertex. Now, of course, instead of calling it an x value, we're just going to call it a t value because that's the letter this equation happens to be using. Not x in terms of the x equation, x in terms of the input value, which is t. So negative b over 2a, the b value is this whole guy right here, a value is negative 16. Type it in the calculator, I'll get about 1.782. So at roughly time 1.782, the ball is going to reach the top of its arc, which that actually confirms what I said in part B, that the ball was probably headed on its way down after 3 seconds because it reached its peak at a little over 1.5 seconds. So at time 1.782 it reaches its peak, but that wasn't the question. The question is, what's the maximum height? I want to know the height of the ball at that point. Again, don't retype things in your calculator. Go ahead and store that for one of your alpha letters, and then instead of typing in 1.782 for the height function, go ahead and type in a for the height function, and you should get roughly 54 feet. So the maximum height of the ball is 54 feet, and it occurs after about 1.5 seconds. Part D, how long is the ball in the air? Well, it's in the air for as long as it's not on the ground. So in other words, instead of asking how long is the ball in the air, I could ask when does the ball hit the ground, which would answer the exact same question. But now it kind of gives me a little bit of a clue. When does the ball hit the ground? Well, that's when the height is 0. So in other words, y equals 0. Set your y equation equal to 0 and solve. Now we could do this the fun way of solving, well, I wouldn't use factoring because there's no way I'm going to get that 135 sine and 25 in the middle. So I could just use the quadratic formula to solve this, or I could use my graphing calculator. Now again, this is a parametric equation originally, but I'm not solving a parametric equation, I'm only solving the y equation. So what I could do is go ahead and graph simply using my y equation. So let's pull up my calculator. Alright, so I'm going to go ahead and graph using only my y equation. Now, right now my calculator is still in parametric mode. I don't need both x and y, I only need one equation at a time, so I'm going to go ahead and put it back in function mode before I graph this. I'll go ahead and graph negative 16 fake t squared plus 135 sine of 25 times t, and before I type, actually let's go ahead and type in plus 4. Before I graph anything, I'm going to remember my calculator was in radian mode, yet this question is a degree, so let's go ahead and fix that real quick. Alright, and before I graph it, I'm going to go ahead and adjust my window. Certain things I've already discovered is that the maximum height was somewhere around 50, and that maximum height occurred after about 1.7 seconds. So I'm going to adjust my window to accommodate for that. X represents your time. So let's go ahead and start at time 0, and let's go as far as time, let's only go 5 seconds down, because it was already on its way down after 3 seconds. So just give it a couple of extra seconds, it'll probably hit the ground by then. If not, we'll go ahead and adjust that. Alright, and then for y min and y max, I like to have a little bit below the x-axis just to make sure that nothing gets blocked by anything on the bottom of my screen. So I'll go as far as -2, which is going to be 2 feet below the ground, and I'm going to go as high as 60 because I know the maximum height was somewhere in the 50s. So let's graph it and see what happens. So there's the path of the ball, maximum height, and then it lands right here. Alright, so I just need to know what time it hits the ground, so I'll just use second calc. I'll find the 0. I'll move that cursor so that it's on the left and right of where I think it hits the ground. I'm going to use the left and right arrow keys to do that. Now right now I could go ahead and hit enter now because I'm already on the left of the x-intercept, but I like to move it a little bit closer just so my calculator doesn't have to work as hard. Now that seems close enough. I'm only 12 feet above the ground. I'll hit enter. That creates my left bound. Now I need to make a right bound, which needs to be below the ground, so I'll move my cursor until I see some negative numbers for the y value. There's a negative number, which means I'm just to the right of the x-intercept. I'll hit enter one more time. No need to guess, hit enter one more time, and it will give me when it hits the ground at 3.634 seconds. Remember, that's scientific notation there. Looks like a -18. Oh, sorry, no, that just says -1 e to the -11. Which is really -1 times 10 to the -11, which is 0. So it hits the ground roughly at 3.634 seconds, which is exactly what I knew it was going to be. Alright, moving on. Let's move this off to the side. A 20-foot wall stands 400 feet from the batter. Will the ball make it over the wall? So really the question is, when the x position is 400, what is the y position? Because if the y position is 20 feet or higher, it's going over the wall. Well, actually, if it's 20 feet, it's hitting the top of the wall, so it really has to be more than 20 feet. So really, I need to know what is the y position when the x position is 400. Well, in order to figure out the y position, I need to know what time it is. So to figure out what time it is, I'll use the x equation, set it equal to 400, and then solve for t. So let's set the x equation equal to 400, divide to solve for t, and that's going to give me 3.2 seconds and change. So I just need to know the height at that time. So I'll store that in my calculator because I'm not going to retype decimals, and I'll plug that into my y equation. When I plug it into my y equation, I get 19.5-ish feet, which tells me that at that time the ball is slightly less than the height of the wall, therefore no, the ball will not go over the wall.